Okay, good morning, everyone. Thanks for joining. Today we're very happy to have Lionel Mason from Oxford. He's going to tell us about geometry of strong coupling for amplitudes and Wilson loops.
I'd like to thank organisers for. Sorry, I'll let you admit the Zoomers. Well, it's a great pleasure to be back in Harvard and CMSA. I've opposed to the VHI now, that's downstairs. I know this is a relativity seminar, but this is relativity in its more general sense. So what I'm going to be talking about is part of relativity whose ADS-CFT, which I guess these days does. And this is a story about amplitudes and Wilson loops in n=4 2p mills. So and it's building on work done by Alday Maldacena sort of 15 years ago. But somehow it was a big splash at the time, but then it sort of petered out, and I felt it was time to sort of come back to it and to really sort of get into some of the details here. So amplitudes and n=4 2p mills have had an incredible amount of effort put into them over the years, and this end of the story was really what motivated a lot of the sort of most important advances. But somehow the actual structures themselves have not been so well explored beyond the initial papers, which are quite stunning, actually. So this is work with Hadley Cross from Oxford, and Emma is now in Southampton. And a sort of a short version, preliminary short version of this is on the archive already, June. And as I say, it's based on work by Alday Maldacena and also Stefan Vieira from 15 years or so ago. And the punchline that I'm aiming for today is not so much a story about the geometry of space-time, which I'm slightly embarrassed to say is what this seminar perhaps ought to be about, but the geometry on the space of data for amplitudes. The main focus here is the space of kinematic data for super Mills amplitudes or Wilson loops, so that there's an identification. And what we'll see at the end of this is new nonlinear and completely integrable differential equations for strongly coupled amplitudes. So that's what that's the new thing which I want to tell you about. So so just to give a bit more of the background then. So there are some remarkable dualities identified in the work of Alday Maldacena, and so that they had a conjecture. Rather stunning conjecture, which was that the amplitudes for n=4 2p mills, which I'm denoting here by this a sub lambda. So these are functions of so the amplitudes here, functions of n momenta in general, and so these could be identified with Wilson loops. Again, functions of these same variables, and the way that works is that what you have is in these k momentas you have a momenta constellation, and this is a story about planar n=4 super mills, and so in planar n=4 super mills, you know what the ordering of these end null momenta are. So the you keep the information not of the group, not the outer element or the color of each of the n particles. That's all encoded just in the ordering. And so these momenta then, because they add up to 0, they eventually, if you just put them end to end in order, you'll get a polygon. And so the claim is then that the amplitude is equal to the Wilson loop, and that's meant to be a statement that's true for all values of the coupling. And then the more perhaps more remarkable story is that if you now think of your space-time as being the boundary of ADS, so maybe in an upper half space picture, you could have your polygon here, and that's meant to be the same thing as a, so this is here, the ADS, and so this is Minkowski space, and this is ADS5, and so the idea is then that the amplitude is given by a Wilson loop, the expectation value of the parallel propagator around this polygon, and then if you then put the boundary condition on the string in ADS5 that it should have a boundary on this null polygon, then that should also compute the amplitude. So, and this is meant to be a statement that the main restriction is that it's planar, n equals 4 super Yang mills, and I guess there's probably even an extension if it was non-planar, you might have to have some generous here. So the okay, so this is something that is sort of remarkable and actually out there, quite out there as it gets. I mean, I guess there were already connections between amplitudes and Wilson loops that were understood in an approximate sense, but that it should hold exactly was a surprise. Now, this is a statement just in ordinary four-dimensional quantum field theory, and and it's as I say, it's understood to be true for all values of coupling. Here, boundary is a tooth coupling, and that's related to the string of the prime and the ADS by this relation. So, in fact, one of the earliest successes of the kind of twistor action approach to scattering amplitudes for n equals 4 super Yang mills was that David Skinner and I managed to prove this relation order by order in perturbation. And that was something that happens in twistor space at the level of the Feynman diagrams. You discover that the Feynman diagrams in twistor space for the amplitude are the planar dual of those for the Wilson loop. So it's quite a non-trivial thing. If you work in a planar limit, the diagrams are planar, and you can then Feynman diagrams. Yeah. Yeah, so this is really not expected because the amplitude is conformally invariant in Minkowski space, and of course the Wilson loop is conformally invariant in this space here, but this space here is where the momentum is. So this was a sort of stunning thing that it implied a whole new bunch of symmetries here, but somehow treating momentum space as if it was Minkowski space, and there was a conformal invariance in this momentum space. So this was something that was sort of really quite unexpected.
Did something to do with T-duality?
That's right. So we T-dualize in the Minkowski coordinates. So what happens is that the
you put them on a circle.
Well, the circle goes to infinity. So it's a little bit of a hand waving T-duality.
But then you verify it.
And so the point is that you actually prove this correspondence between amplitudes and Wilson loops in perturbation theory. And as I say, you can do it at the level of the Feynman diagrams if you run diagrams and twists. But just a story about the way that the superconformal symmetry works is interesting because the superconformal symmetry for the amplitude is different to that for the Wilson loop, and together they generate a Yang. And this is meant to be an expression of the piece integrabilism equals 4 super Yang mills. In fact, you have this Yang. So just this first equality was something dramatic. That just to have that as a conjecture coming out of this work. Let alone the more dramatic statement here that sort of isn't confusing by looking at string theory and ADS. Okay, so this was big news, and the dual conformal symmetry went a long way to helping us solve an awful lot of n equals 4 super Yang mills. But as I say, this identification with the string is yet another step beyond. And the
But that would have been understood earlier.
well, I guess this relationship between Wilson loops and strings is something which Juan, I guess, had at the beginning of the 2000s. Yeah, or maybe before. I'm not sure. And yeah, so but anyway, I mean, I was brought up to be skeptical of ADS-CFT by Roger Penrose. This is something one of these things that he just didn't want to believe it. And this was what really convinced me that there really is something there. Because what Alday Maldacena did was that they said, okay, well, let's go to strong coupling. Let's take alpha prime to 0, so you can actually do the string computation. And this is strong coupling, so lambda goes to infinity. And if you do that, then this string theory in ADS becomes relatively straightforward. I mean, it's not easy. You've still got to think about minimal surfaces in ADS. But the claim is then that in that strong coupling limit, the expectation value of this Wilson loop is e to the minus area of the minimal surface here that spans polygon. And that they did rather a tour de force, an analysis of this, using integral systems. I'll tell you a bit more about how that works later. But one of the things that I found boggling at the time was that there's a lot of divergences in the story. This area here, which is what you have to compute, it's going out to infinity, and it particularly has infinities associated with the cusps. And they were able to sort of control these, evaluate these. You just go up a little bit into ADS, and then it becomes finite. And this agreed precisely with conjectures from the amplitudes community, which were really heavy-duty conjectures. I mean, these are not simple expressions. There's lots of logs, dialogues, and so on, and they could get them all. And it was really precise. And in fact, I guess Marcus is part of the story here. There's conjecture, EDS conjecture for what the amplitude was to all orders, and Alday Maldacena said, no, just a moment, there's a little bit more here. And so 4 points and 5 points, this BDS conjecture had to be correct by dual conformal invariance. But then at 6 points, I think they predicted something would go wrong, and Marcus did a heroic calculation with his team and verified that indeed something did go wrong with the BDS conjecture. So the interplay here was really very stunning and really gave a lot of confidence in these conjectures here. So okay, so this is to a certain extent ancient history, but it's rather well, yeah.
I'm curious. What's the analog of this some little equal string goal sheet we all gave something like celestial problem?
Well, I'll ask Andy. Sorry, sorry, I'm not sure.
I like that. I was asking, how did you motivate? How did you found this motivated? There's a string goal sheet that has to be bound to do something with, say, a D1 brain or some other object. What's the argument that is the fundamental string?
Again, I think there are other people in the audience more expert than me on this.
Well, I think there's, of course,
yeah, I mean, I think you think of the Wilson loop as being charged, heavy particle or something in general, and that source of the string. Is that right? I mean, that's, yeah.
And the first line is independent of string. The first equality.
Yeah, the first equality is independent of string theory, but you wouldn't have thought of it without T duality. You wouldn't have thought of it certainly as an exact relation. There were already ideas in the literature as how limits, soft limits, or something of scattering amplitudes could be related to Wilson lines. But to have this very, very precise relation, which is where this is really a term by term equality, that was new. Any other questions?
And presumably that exact equality is only for any.
It's only for planar n equals 4. I mean, there are.
Approximate.
That's right. Yeah. I think that's right. So these kinds of it wasn't unprecedented, but to have this as an exact statement is sort of new.
Is this kind of matter when you also compose and thing?
Yeah, I mean, this in this case is coming from a very specific string duality, T duality, and it's also coming from integrability, which is what I'll be talking about in a moment. Okay, so what I want to talk about then is this last story then. So I'm going to be my shame I gave this talk in Princeton as a conference on string theory at finite alpha prime, and the first thing I did in the talk was to set alpha prime to 0. So that told off. I see. Is that, so is it alpha prime goes to infinity? I'm not sure. What does T duality do to alpha prime? Yeah. Okay. Well, better come back at the time. But still, okay. So. Okay, so the output of today's talk is going to be a statement about the space of kinematic data Wilson loops. So here we're just talking about n null vectors joining up with momentum conservation. But in the amplitudes world, this space of kinematic data has been sort of much studied and reformulated in a way to make its geometry much richer and more interesting. And so I'm going to talk about the case where the kinematics are restricted today, where rather than having it be in M4, it's actually just going to be in 2-dimensional space. And but there's a completely analogous story for the 4-dimensional case. And in both cases, what you have is something that's known as a cluster variety. So this is important because amplitudes are very complicated functions. They tend to be logs, polylogs, dialogues, and so on. And you need to know what the arguments of those are meant to be. And cluster varieties have special coordinates which encode polylog identities. In this case, the spaces of kinematic data are very well-known cluster varieties. In this reduced case, and what you find is that the so first of all, you discover that every null polygon in 1 + 1 dimensions has 2 sides, because there's only 2 null directions. It's left moving, right moving, and it's easy to explain yourself that you can't have a lot of number of sides. So I would always be talking about a 2n-sided polygon. And in fact, because there are only 2 types of light rays, every other light ray will correspond to a fixed value of x minus. So all of these ones are fixed values of x minus, and the other ones are fixed values of x plus. So what you end up with is n copies of so there are n x pluses and n x minuses to describe this light polygon. So we're labeling the edges of the polygon alternately by constant x plus and x minus. But we have that this thing is conforming invariant. So because we're talking about n equals 4 super mils, n equals 4 super mils is conformally invariant, and that conformal invariance comes down to SL2R on each of the x plus and the x minus factors. And what that means is we think of each of these xi's, x plus or minus, as really living inside a real projected line. We can do an SL2R transformation, or Möbius transformation of it. And you've got the x pluses in here, the x minuses in there, and we expect any invariant like the area of the Wilson loop to live to be conformally invariant, and so it actually lives on this quotient space. So this here is endpoints minus the three-dimensional Möbius group, so it's n minus 3 dimensional. So that's the let's say. Oh, sorry. Yeah. So I'm going to work here in M2 for the purpose of this talk. There's an analogous story for the four-dimensional case, and in that case, the analogous story there actually is the Grassmannian of four planes and n dimensions, or it's really n twistors. So if you want to do this in four dimensions, you would have n twistors, n four component twistors up to the the conformal group. Well, super conformal group. So yeah, so this is really doing twistors in 1 plus 1 dimensions. So they're fairly trivial.
What's the line between x plus and x minus?
So so each side is a lightweight. So this side here is a constant x plus, and this one's an x minus, constant x minus. So you got n of these and n of those. That gives you the.
Presumably completely.
Well, we are taking the quotient to get to the n naught 10. The quotient, sorry, quotient by the so this is all in the bound. This follow these in the bound. So, and so then we're going to be thinking about the spanning minimal surface in the ADS3 in this case. So anyway, so the key thing I want to move on to now is to explain in what sense these cluster varieties. And I just the theory of cluster varieties is quite elaborate, so I just want to do this in a very kind of naive way. So cluster coordinates on n naught n are well. So we want to have invariant functions, and invariant functions made out of cross ratios. And there are many cross ratios you can form. You just basically take 4 points on your IJKL and form a cross ratio. So, but what you want to do is you want to form them in such a way that you actually get a nice set of coordinates on space. So we actually only want to take n minus 3 of them to get a coordinate system. And these come in clusters. And the clusters we're after can be just combinatorially identified with triangulations of a n-dot. So here I've done a zigzag triangulation of an n-dot. And then the way in which you set up your clusters is that you identify a cross ratio with a chord. And if you count the number of chords in the triangulation, you get n minus 3, which is right now. And so here is how the chords in the zigzag are related to cross ratios. So the one joining I to j, this is what you get. More generally, it's just your triangulation, the chord sits inside a square, and you do a cross of the square. So there's but this is how you do it, the zigzag triangulation. And there's a rule for what you do if you want to go from one cluster to another cluster. You can do it by flipping chords. So that is to say, that chord there could be flipped to that chord that way. And then there's some relations between the cross ratios. There's some simple polynomials which give you what's known as a mutation. The other thing that I'm going to need from this theory is the fact that these cluster varieties have Poisson structures and two forms.
What exactly is a cluster?
What exactly is a cluster variety? I guess the trouble is, if you've been to talks on cluster varieties, they will give you such a half the talk can be set up defining everything. So you can write down a quiver, and then you can write down active nodes, and inactive nodes you can write down mutate. So what exactly is a cluster variety? I guess they're toric varieties. I'm not sure. Are they all cluster varieties? Marcus is the expert. Marcus, what's a cluster variety in general?
Generated by cluster variables generated by this computation process.
Yeah, I'm sorry. I wish I could. Yeah. Okay. Okay, but what's going to play a big role later is that these things actually all have Poisson structures and two forms, which in happy situations are simplex, non-degenerate. And so given the cluster, it has constant coefficients, and there's epsilon RS being plus or minus 1. But the zigzag is given by this, but more generally it's associated with when R and S are in the same triangle, whether you have to go around clockwise or anti-clockwise in the triangle. And one of the key points about this is that this two-form or Poisson structure, and there's you can do an inverse thing as well, it's mutation invariant, as long as you get your definition of these epsilons correct. And that's going to play a big role in what follows. So okay, so that's my cluster varieties on one slide. So, okay. So now we've got a sort of now we're talking. So this is the way of parameterizing all of these polygons. How are we going to go about solving for this minimal surface that's going to sit on it, that's going to bound this polygon? And lots of beautiful things happen when you start studying that story. So it's been well known since early days of ADS-CFT, well, probably been well known since the 60s, that minimal surfaces in cosmological constant one spaces, homogeneous spaces are an integral system. And in this case, where I'm dealing with restricted kinematics, it's actually a very famous one. It's the Shine-Gordon equation. But you do have this extra function in there. You can get rid of it with the conformal transformation, but we'll keep it for the time being. This extra P of Z here, in our context, is actually going to be, it could be an arbitrary holomorphic function, which you could get rid of with the conformal mapping, but we're going to keep it, and it will be a polynomial in Z. And the point here, which is completely counterintuitive, is that the minimal surface is actually a world sheet. The minimal surface world sheet in the standard sort of induced conformal structure is actually a Riemann sphere. And this here I've drawn it in such a way that it looks just like a disk, but in terms of its because it's going out to infinity, it's actually a Riemann sphere. And the boundary polygon is somehow encoded. Sorry? Yes, so the boundary polygon is encoded in the irregular singularity at Z equals infinity. Is that what you were trying to say? There's a point missing Z equals infinity.
What's the term again now?
So I'm working in a signature where this picture isn't really appropriate. I'm still thinking about the Rentz signature boundary, but but I'm thinking about the situation in which the minimal surface is space-like. So the minimal surface that spans inside the space-like. So there's a kind of Euclidean region where the planes, I mean, they're curves, but so I guess just the thing that's confusing when you the polygons have to go all the way around you. Or yeah, so this picture isn't sort of really that. It's sort of it would work in maybe Euclidean signature version. But in Euclidean signature, you couldn't have a null boundary. Okay, so what you discover then is that the boundary polygon is really encoded in some sort of singularity as in z equals infinity. And this P of z here, if you've got a 2n-sided polygon, this is going to be a polynomial of degree n minus 2. And in fact, this is best thought of as a coefficient of a quadratic differential. So it's a quadratic differential of the polar border n plus 2 at infinity. And on the next slide, I'll talk about a Hitchin system, which has an actual quadratic differential associated. So the idea then is that these coefficients here of this polynomial are actually secretly encoding the boundary basis. And they give complex coordinates on this space of the matter base. And so Alday Maldacena argue using integrability methods that there's a unique solution for each choice of these n's or chi's, and but this is something that you will only really believe in this kind of Euclidean region where the surface is forced to be space-like by the zigzagging. So they also argue or show that this space of data, this now has these complex coordinates n, and in fact it's naturally Kahler in those coordinates in such a way that the regularized area, which is the main quantity we want to compute, is a Hamiltonian for the circle symmetry, which just rotates all the ends. So that's slightly wrong. Okay, so then your task here then is actually to compute this regularized area. You want to compute the amplitude, and you could sort of get it in these n coordinates by knowing what the Kahler scale was. So there's an elementary formula for this. So that's the first sort of geometric statement that they make. So these ends contain the data of the cross ratios.
So what is alpha?
Alpha is going to be a function on the world sheet that's uniquely defined by the differential equation about functions.
Is it going to be the area?
Well, it determines the metric on the world sheet, the restricted metric on the world sheet with which you compute. So the point is that if you're less interested in the amplitude or the Wilson, you want to forget about the components, about the alpha. But in this world, you'd have to solve the equation and integrate to get the area. So how do you bypass that? You start using some integral systems technique. And so it's been known for many years that minimal surface and ADS have got a lax pair, and this introduces an auxiliary complex parameter. So this isn't the world sheet parameter, this is the parameter for the lax pair. And in fact, that Alday Maldacena show that this is closely related to some very famous integrable systems, Hitchin systems. So what they show is that in this strict kinematic case, it's gives an SU2 Hitchin system that's Z2 invariant, or in the full ADS5 case, you get an SU4 Hitchin system that's Z4 invariant. So you have sort of, it's a discrete symmetry reduction of a Hitchin system. And then just to state kind of the key steps in their analysis, the lax pair is a pair of operators on the world sheet. So this L of zeta looks like an operator d by dz plus sort of a, which is depends on z bar and zeta. I'm going to write it out properly. And a d by z bar. Silver, etc. And so on the Riemann sphere, then these operators on the Z sphere, these operators inherit this sort of irregular singularity at n equals infinity, and this is now an irregular singularity in the sense of Eisenhower. And because it's regular, you haven't just got a monodromy around the infinite point, but you've also got a whole bunch of Stokes states. And so the idea is to actually encode the whole solution into the Stokes data. And this is something which is sort of standard in integral systems. And again, we'll take whole lectures to talk about in detail. And so basically what happens is that near z equals infinity, you get a bunch of Stokes sectors on which you have different solutions to the lax pair, and the small solutions correspond to the size of the polygon. And but because you've got this extra parameter in there, the Stokes data and everything depends on this auxiliary function zeta, auxiliary complex variable zeta, and that's where the magic of integrability is. And so you forget about Z and you just think about this auxiliary complex parameter, and suddenly you can encode everything. So I'll say on the next slide how that happens, or what the output is. But before I get there, just this connection with integral systems is suggestive of interesting geometric structure. So it's been well known since the 80s that moduli spaces of ordinary regular Hitchin systems are hyperplane manifolds, and they're integral systems in their own right. And in fact, for me, as a kind of twistor theorist, I get excited because I like hyperplane manifolds because they have twistors. And so is there a twistor construction for this moduli space? The moduli space being this space of kinematic data. So with these irregular singularities, this story gets harder. It was studied by Kahler and Bolch in 2004, but they didn't do this case. So they didn't do something that applies to that. So one has to sort of use stuff that's out there. But the people who did do stuff that's closely related are Gaiato, Moore, and Nietzsche. So they did do irregular singularities for Hitchin systems, and Gaiato, as you see, was part of this team here and could educate them as to how all that integral systems law could be applied. So let me just, as I say, many long papers back in the day from 2007 to 2010. But what was the output? So the output was what's known as a Y system. So when you name something after a letter in the alphabet, it means that you're probably buried in your own notation. But bear with me. So what is a Y system? So a Y system is going to be n-3, in our case here, it'll be n-3 complex functions Y, and these will depend on the kinematic data, these cross ratios chi plus and minus, but they also depend on the spectral parameter. So this stage, we've forgotten about the Z of the world sheets. That's gone. These are sort of more like sort of Stokes. And so these Y's enhance the original cross ratios, chi plus and chi minus. And so when you put z equals 1, it will give you the chi pluses. And when you get z equals I, you'll get the chi minuses. And so this gives you some extension of them. And the key point is that these are actually analytic in zeta, but they with known singular structure. So they have a branching singularity at z equals 0 and infinity, and a cut that joins them up along the negative real axis. So I guess I could. So this is now the zeta plane, and you imagine a cut going from 0 to infinity, where it's branching. And as it approaches the branching singularities at the origin or infinity, it's basically behaving like either 1 over zeta or zeta, it's leading order. So if you want to specify the analytic structure completely, though, we've got to say what it does as you cross the cut here. And as you cross the cut, so one way to say it is that we've got an analytically continue by zeta goes to minus zeta, and that will give you that will sort of move the cut the other way. And once you've done that, the relationship between the analytically continued y's and the original y's are these the y system relations. And in modern parlance, this is just a system of mutations for the cluster prime. And in fact, what it is a system of mutations that correspond to the cluster mutations system. So it isn't just one cluster mutation, it's a system of n-3 cluster mutations that correspond to rotating your polygon by 2 pi by n. So that zigzag gets rotated to a different zigzag. And this is a mutation that takes you from one set of cluster coordinates to the next as you rotate the polygon. Yeah.
So in the Y system, what is special about the zigzag triangulation?
Nothing. Okay. So I guess well, I mean, the formula looks like this in the zigzag. Yeah. But
switch to a different set of.
Yeah. So this is the sort of this is the sort of discussions that Hadley and Omar and I are having. So let's write this in grown up sort of 2020s language rather than sort of 2010s. So, yeah. Okay. So the so that's what they produced though. That was back in the day, 2010, and what do you do with it then? So the intuition is then it's applied math, so it's an intuition rather than a theorem. You now know what these functions y are doing at every point of the complex plane. You know how they behave at 0 and infinity and how they jump across the branch. So they're rigidly defined. It's a sort of some extension of Liouville's theorem tells you that there exists a unique set of y's given that list of conditions. And you can actually firm this up by writing down the Plebanski beta ansatz, and then that's an integral equation, and that certainly converges into certain regions of the Cantor space. You can prove that quite nicely and do it. You can put it on a computing variable. So that works very nicely. As it stands, the way that this is set up is a bit clunky. So you know, the easy way to set up the y system is in terms of the z's. The z's are related to the chi plus or minuses, but they are complicated functions in general. So asymptotically, they have some agreements as chi plus minus goes to 0 and infinity, but it's hard in general. And then you have, they gave us an integral formula in terms of the z's. So the whole system closes, and it gives a complex analysis procedure to construct the amplitude, but it's clunky. You've got to construct the y's in terms of the z's, but you get the coordinate transformation from the z's I plus minuses, and then you've got to find the r bar this integration. And so you ask the question, well, can you say something more directly? What does it mean for the geometry of this space? So, okay, so this is where so for people who are allergic to twistors, this is only one slide. Sorry, Aston was telling me that yesterday I had to strip out all the twistors. So today I've got one slide. So the point is that I said that the Hitchin systems have hyperkahler moduli spaces. Hyperkahler moduli spaces have twistor spaces. And so what does this Y system have to do with the twistor space? Well, in some sense, it is the twistor space. So what do I mean by that? So the twistor space is really just this kinematic space of kinematic data across the Riemann sphere, where the Riemann sphere is this zeta coordinate, this spectral parameter from the integral systems. So it is like this product of two cluster varieties across the one. And these are smooth coordinates on the twistor space. But what the Y system does is it gives you holomorphic coordinates. So that is to say, the Y's and zetas, the Y's and the zeta, give this twistor space the structure of a complex n-2 manifold. And there are various things you can say about this complex n-2 manifold. It has a projection onto the Riemann sphere, projecting onto zeta. The fibers are copies of n0 nc, and the fibers have a holomorphic symplectic structure when n is odd. So when the fibers are such, this is really the condition that the fibers are really fibers have. And so this is the sigma that I wrote. And so this is obviously non-degenerate only for the case where n is odd, because that's the case when the fibers are actually conventional. And so when you stop at that point, this is actually the list of criteria to have a twistor space for a hyperkahler manifold. And you can just read that off from knowing this connection between the Y system and twistor space. And then the final point is that we have this circle symmetry action I talked about before. So this you have this global holomorphic vector field B tilde, which in the Y zeta coordinates is just easily by the zeta. The Y's have been sort of normalized in such a way that they vary by this. So now you see it's just rotating the zeta plane. And in the world of Hitchin systems, you have a Higgs field that you can rotate by ECI. So it's a familiar circle action from Hitchin systems. And then well, this is the one we were talking about before, which determines the circle action in whose Hamiltonian is the actual area of the Riemann surface, area of the minimal surface that you're after. Okay, so that's the twistor theory. Is that any questions? No, okay, I expected there to be a blank side as well. Okay, but you don't. I don't need to tell you too much about the twistor theory. The way you get the geometric structure out of this is now, in some sense, a well-ordered machine. So the key idea is that this symplectic form of the fibers, this sigma zeta, it doesn't branch on the Riemann sphere, and the reason it doesn't branch on the Riemann sphere is because it's preserved by the mutations, and the mutations were what glued the jump across the cut. They were told you how to go across the cut. Just to be a bit more, well, and also we know about the asymptotics as zeta goes to 0 and infinity. So we can actually just determine what this thing has to look like. In fact, just the asymptotics tell us that sigma has double poles at zeta equals 0 and infinity, because because the log y here, actually a log panographic y has sigma. But in fact, the Y system is a bit more subtle than that. It's really telling you what was happening between zeta and minus zeta. and this form is actually invariant under theta goes to minus theta. So we only get 1 over theta squared, order 1, and order theta squared, and we can expand it like this. This gives us the generic. There's only 3 forms that we have to identify this, and these forms sigma 1, sigma I, and omega will be independent of theta. So that's the start, and then the fact that the y's are given by the cross ratios of 1 and I allows us to actually, so I've written this in this way, so you can actually identify the sigma 1 with just the, well, this is actually the d log chi pluses, and this is the d log chi minuses. And then the fact that this came from something which was just, this obviously has rank no more than n minus 3, because there's only n minus 3 sort of d log y r's. And that condition gives you the fact that the this last omega, which is all there is left to identify, is actually pseudo-Kahler in these log chi plus and log chi minus coordinates, and it also gives you this equation here, this Monge-Ampère equation. So this is a pseudo-hyperKahler system. So it's a hyperKahler system written out in a split signature. And this J here that's going to determine the omega is the Kahler scalar for this pseudo-hyperKahler structure. So that's what that's what you obtain from the twistor theory following kind of standard law. But things are a little bit better than that, actually. So this J a priori is, I mean, it will determine everything, but it could do it in a nasty nonlinear way. But let's just push a bit further. So Alday Maldacena told us that the remainder function, the area of the normal surfaces, was that Hamiltonian with respect to the Kahler structure in the m coordinates, but in fact in these coordinates, the Kahler structure is this already known sigma 1 plus sigma I Kahler structure, where sigma 1 and sigma I. So these, add these two together, and that gives you a symplectic form. And so what you learn is that this R is a Hamiltonian for the circle action symplectic form. And so you can start putting that in and putting in the condition that the circle action is a symmetry. And what you discover is that this J that I wrote down on the previous slide is precisely the R. And so that's telling us already then that the remainder function, or the area, the finite part of the area, is satisfies this Plebanski equation, and it defines a pseudo-hyperKahler structure on this space vector. So we have these symplectic forms. Basically, you have 3 symplectic forms. And you also have an S1 symmetry that's defined by the vector field, which is the Hamiltonian vector field itself. So that together gives you a closed system. And this is sort of now by standard law, it's a completely integrable differential equation with a max system, which is which you can read off actually from all the structures we have. So all of these operators have to mute, and that determines these differential equations.
Monge equation of the function not null.
No. So the connection with so at some point I think you know, because they were talking to Garza and Greg Moore and things. I mean, the connection with hyperKahler spaces was sort of hinted at, but then the Z2 invariance was thought to be just giving you a real slice and sort of was throwing away the hyperKahler structure. So, and this, I mean, it is a point here that these are not the ones that GMN have. So if you actually try to compare this, the GMN hyperKahler structures, these are quite different. Okay, so that's the main punchline, though. Out of identifying the Y system with a twistor construction, you discover that this is a way of expressing the twistor theory for the Hitchin systems, and you discover that the remainder function you put, yeah.
Sorry, just to be clear, is this a statement, if we go back, is this a statement only about the leading order at large lambda?
Absolutely, this is all just the strong coupling. And yeah, no, I'm so sorry. I mean, it'd be so great if I could be given the entire. Yeah, no, that's yeah, but of course, yeah. Next time I give a lecture, I'll have all the corrections tools. No. Okay, so anyway, but the summary of the geometry here is the remainder function, the area of the minimal surface, or the finite part of the area of the minimal surface, is essentially a Kahler pseudo-hyperKahler scalar for a pseudo-hyperKahler geometry on the space of the matter basis. And this enhances the cluster geometry. Everything about it sort of just ties in with the Poisson structure of these varieties. It has a circle symmetry, but it's not manifest in these pi plus minus coordinates. There has been some analysis since the 2010 paper. It sort of petered out actually after a year or two. I mean, so it's amazing looking at literature that it just stopped. And it's partly because of the convoluted nature of the problem, the way they set it up. And but there were some remarkable things actually came out a little bit later. So even at the time, there's an orbifold point in this space, which is the regular polygon, and you can expand around it. So a Japanese group does expansions. People sort of study the TBAs. One of the things I haven't said here is that when you study the TBAs, you can write down the two-loop answer, and you can write down the large the lambda goes to infinity answer. You put them on a graph, and you have to look at it very closely to see the two different. So it's already almost there. Two loops, you're already almost at the strong coupling answer. I mean, this is maybe just one parameter, so who knows whether it's true for parameters. One way to understand how these things link together, we've got one of these varieties for each n, just with those restricted kinematics. But then what happens is that you can degenerate down to sort of n-1 with a collinear limit. So you push that down to there, you get a collinear limit. And in fact, in this restricted kinematics, you actually lose two, because when you lose one, then two other geodesics line up and they become the same. So you lose two sides at a time. And so you have a nested boundary structure. And the R, the renormalized area, once you take away some log terms, is going to be smooth in these collinear limits. And the geometry again has a hierarchical structure. So I was really talking about n odd to get the hyperKahler manifold, but the geometry then even follows from the geometry of such a mix. So that will give you some geometry there. And more generally, one would like to see that the hierarchy of nested boundaries determines the full solution. You come down to the octagon, which is determined by the degree of metric, or at least some limit of it. So it's a non-trivial thing. You've got these. You might have thought that there's something trivial going on in these geometries, but they're not trivial. They're complicated functions, and there are numerics out there. And but the explicit formulas even the octagon at that time. So all of this sort of goes through. The cluster varieties are well known in for the full kinematics, and the same argument should go through. You expect a full hyperKahler variety or pseudo-hyperKahler variety when the dimensionality is divisible by 4 at least, and then you could hope you get other others with other maybe special geometry something like that, some related geometry for the other values of n. Special K classes. So that would be an subspace. And so is there a role for this, even if we, so Marcus wanted me to actually do the full string theory in ADS, which obviously will happen at some point, but maybe not this year or next year. But can you get anything out of this for more general amplitudes? And there are some hints from the origin story that Mark Dixon and Benjamin Basso coming up with, which really relates the full amplitude along certain sort of special subspaces to what's going on at strong current. So they have some guesses and conjectures. I think might be able to get some insights. And more generally, I mean, so I've already said that you get very good numerical recoupling, but more generally, the Y systems are standard structures in quantum integrability. And so I can see these ideas having a broader application. Put a stop there over time. So thank you very much.
All right, if there's maybe one quick question, and then
well, this is really a bulk ADS thing in the sense that it's well, I'm not sure. You see, I mean, the actual parameter space is, of course, the space of boundary conditions. But it is, this R is the area of the renormalized areas.
So the ADS must somehow code this
absolutely. So this is a sort of version of ADS CFT where you don't deform the metric on ADS. You just see all you get inside ADS is a string. So it's a kind of a slightly kind of so it's a parameter or a choice of scale in the ADS CFT correspondence. So yeah. But you see, the point is you don't want to know what null says. Yeah.
Sorry,
Sorry. Well, I mean, so these moduli spaces are all just n naught n, the real n naught n, two copies of them. AK is n naught k plus 3. Yeah. So these rates, but of course, if you want to do this in the full kinematics, you'd be dealing with G core n. I'm not sure what you call that. Yeah, so okay, so N1N, D type is the case you get the form pack. Let's do form pack. Yeah, so the D type stories.
all right, let's thank Lionel again.
And then